In this video, we're going to solve a problem from matrix and determinant which appear in the year 2005 in JEE main paper. So let's go ahead and understand the problem statement. Here it says that we have a given matrix and it says 6A inverse is equal to A square plus 6A plus DI, and we need to find out the value of C and D, right? That's it. Now notice that, right, to find out this problem, right, the one method should be, right, we find the A inverse matrix, then we find A square matrix, and then we equate, right, that 6A inverse A square 6A and all that stuff, right, and then equating element wise, right, we'll find the value of C and D. So that looks very straightforward, but obviously, right, this technique will takes little bit of effort, right? So we'll solve that method in a different way. So let's go ahead and observe how we solve it. Let's proceed. As we see, right, we have solved this particular problem in a different way. So first we try to understand two basic concepts in matrix. So first one is characteristic equation for a matrix. What's actually that? It says that for any matrix A of order n cross n, it should be square matrix. The characteristic equation is determinant of A minus lambda in should be 0. Okay, so basically we have to identify, or we have to find the matrix A minus lambda in, and then we have to find the corresponding determinant. When we find the determinant, then that called the characteristic equation. Now here In is the identity matrix, obviously we know that. Here the characteristic equation will be a polynomial, right, of degree n. So whatever the degree of the matrix, the degree of the polynomial will be that. So if we expand, right, we can get that characteristic polynomial will be n lambda n a n minus 1 lambda n minus 2 and so on and so forth, right? That's it. So now why we are discussing that? Because there is a theorem which known as Cayley-Hamilton theorem. So this particular theorem states that every square matrix will satisfy its characteristic equation. That means that instead of lambda, if we substitute A, right, the matrix A, then the equation will be satisfied. Okay, that's the Cayley-Hamilton theorem. So now let's proceed. Let's go ahead. Now we consider the matrix, that is a 3 cross 3 matrix here, and we say that we need to find out the characteristic equation. So that's why we consider a identity matrix of order 3. Now we need to calculate A minus lambda I3. So now see that, right, only the diagonal elements will change. So it's became 1 minus lambda, 1 minus lambda and 4 minus lambda. What is the characteristic equation? The characteristic equation says that it's actually the determinant of this matrix. So let's go ahead and find out the determinant by expanding that with respect to the first row. Okay, let's go ahead. So if I find the determinant, right, and expand with respect to the first row, we see that, right, it will be 1 minus lambda multiplied by 1 minus lambda into 4 minus lambda minus 2 into 1, and the change will be signed. Okay, that's it. So that gives us the determinant, right? Now we just do the basic algebraic calculation, right? So we just multiply and do our simple calculation. So we'll get obviously a cubic equation, right? So let's see that step only the difficulties in this particular problem, and it's very simple. So if we go ahead and get that multiplication of 1 minus lambda and lambda square, 5 minus lambda and 6, we get a cubic equation. Okay, so after simplification, right, we get the final characteristic equation as lambda cube 6 lambda square 11 lambda plus 6, right? That's it. So here the coefficient of lambda cube, we make it 1 because it looks good, right? That's it. So we get the characteristic equation of this given matrix A. So now let's proceed and use Cayley-Hamilton theorem. Let's go ahead. So here, after obtaining that characteristic equation, we'll apply that Cayley-Hamilton theorem. So therefore, that polynomial where we have see lambda, it will be replaced by A. So it became A cube minus 6A squared plus 11A minus 6I. Now see that I cannot write, or you cannot write that 6 here, right? Because as it's become a matrix equation, so this constant 6 will be converted to I, where I is actually identity matrix of order 3. That's the only thing we have to remember. Now take care of that. See that what we are going to find out, that 6a inverse. So that's why I rewrite the given matrix equation, right, in such a way that 6i in one left hand side and everything else in the right hand side. Now as we need to get 6a inverse, so we multiply both sides by a inverse. So if we do so, right, it becomes 6a I a inverse, a cube into a inverse, and 6a square a inverse, 11a inverse. We know that, right, for any matrix, right, that a cube a inverse can be written as, right, a square a into a inverse, a square will be converted now a inverse, and so on. For any matrix, right, A and A inverse should be identity matrix. So therefore, we can write 6A I A inverse is square I minus 6AI and 11I. Now also we know that if we multiply a matrix by the identity matrix, the matrix multiplication will give the same thing, right? So A into I will be A. So therefore we get it 6A inverse is equal to A square minus 6A plus 11I. Now notice that we already obtained the given relation, right? So if we compare, right, with that given relation, we can easily obtain C is equal to minus 6 and D is equal to 11. So therefore, we obtain that in this particular problem, option A is the correct option. And that's it. So this is a direct application of Cayley-Hamilton theorem. Remember that, it's very useful. Hope you understood it. Thank you.